What's up, my beautiful viewers and subscribers? Welcome back to another video. This is JK Engineering and Architecture coming to you with another video. In this week's video, my topic is going to be structural analysis. In my last video, I have introduced to you what goes on with structural engineering. So I didn't think I've mentioned to you who is a structural engineer and what a structural engineer uses to design any structure. So a structural engineer is a person that uses scientific and mathematical means to solve engineering problems as well as to design structures. So they use physics and mathematics to do that, to design your beams, your columns, your footing, a bridge, a tunnel, whatever the case might be as it relates to structure. And when you see the word structure as it relates to engineering, it means a system that can carry loads. So in this week's video, I'm going to take you through the structural analysis, how to calculate the formula to work out the maximum bending moment for a beam which is acted upon by a point load. So if you look at this beam, this is the beam here. The beam has a length of L and we have a load of P acting towards the center of the beam, or otherwise known what is called the center of gravity. So remember, I've said to you that in order for any structural system to maintain its equilibrium, the sum of the forces that are going down must be equal to the sum of the forces that are going up. So we have here, we have a load of P coming down at the center of the beam, and at either end of the beam we are going to have P over 2. So if you observe, at this end the reaction is going to be P over 2, and at this end the reaction is going to be P over 2. So P over 2 plus P over 2 is going to give you 1, and it must come back to the load P, right? So if it is acting at the center of the beam, that means that half the load is going to act on this side, and the other half is going to act on this side. So one half is going to act on the left, and the other half is going to act on the right. And the distance between the reaction here to the center of the beam is going to be L over 2, and we're going to have L over 2 on this side as well, since the entire length of the beam is L, right? So that pretty much sets it up for the beam. So I'm going to show you now how to calculate the maximum bending moment of this beam carrying out a load of a point load acting at the center. So the reason for calculating the maximum bending moment, or the formula for the maximum bending moment, we're going to use that formula to calculate the area of steel, or the amount of reinforcement that is going to be needed to withstand this load of P. But that is for another video when I start actually goes into the beam design. This video is about structural engineering as it relates to a point load. So if you look now, we have P over 2 going up, P over 2 going up, and we have P coming down. So I'm going to plot what is known as the shear force diagram. So we're going to plot two diagrams, the shear force diagram and the bending moment diagram. But first we are going to look at the shear force. So our shear force diagram is going to look something like this. So that is our shear force diagram, right? So we have a force going up here of P over 2, and we have this length from here to here, which is going to be L over 2. So we're going to have P coming down here, and we're going to have our distance here of L over 2, and we're going to have our force going up again as P over 2. See that? So this is our shear force diagram. Shear force. Now we're going to plot the bending moments diagram now. Alright? So the bending moments diagram is going to look like this. And this is our bending moments, right? And since it is a point load, the bending moments diagram is going to look like this, because it is a point load. So imagine you have a ruler. So this ruler represents the beam, and the beam is impacted by a point load at the center. The behavior, when that load is acting down on the beam is going to tend to behave like this. So this is why the bending moments diagram looks like this. So we're going to calculate now the bending moments diagram, right? The maximum bending moments for this beam, which is going to be this distance, or the point right here, right? So the point right here is going to be the area of this rectangle, right? Or the area of this rectangle. So the area of this rectangle, the area is going to equal to P over 2 times L over 2. So it's going to be P over 2 times L over 2, which is going to equal to PL over 4. So the bending moments is going to equal to PL over 2, PL over 4, sorry, PL over 4 for a point load. So if you're in the field and you want, or if you want to calculate the bending moments diagram, you do not have to go ahead and plot the shear force and bending moments diagram for this point load if you know that the bending moments is going to equal to PL over 4. I'm going to put some actual figures to this and let you and demonstrate to you how it is necessary to know the formula PL over 4 for a point load, rather than going through the analysis like this, rather than drawing the shear force and the bending moments diagram. So the bending moments diagram here, the maximum bending moments here, is going to equal to PL over 4. So to recap what I've just did, I have just demonstrated to you how to calculate the formula for the bending moment of a point load. So this is the beam, as I was mentioned to you before, right? This is the shear force diagram, and this is the bending moments diagram. Now, in structural analysis, if you actually know the formula to calculate the bending moment for a point load, you do not have to go through this format. But this still is a useful format to know, because not every time you're going to be encounter a beam with a single load. At times you're going to encounter beams with uniform distributed load, point load at the center, and point load off the center, and uniform distributed load off center as well. And you have to go through this to calculate the maximum bending moment for that beam system. So, but if you're going to deal with a single point load or a single uniform distributed load, it is best for you to know the formula. And as I've said to you before, the formula to calculate the bending moments for a point load is PL over 4. So that is it for the formula for the bending moments for a point load. So now I am going to put actual numbers to this beam system to demonstrate to you how the formula is applied. So therefore, here we have a beam, a simple supported beam. And by the way, when you're designing beam, the first thing you should take into consideration is the beam end condition. So you have to identify whether the beam is simple supported or the beam is fixed at both ends. So you have two different ways, or you can calculate the bending moments for a beam, a simple supported beam, and a beam with its ends are fixed. I am going to get into that in future videos, but for this video in particular, I'm just going to go over a simple supported beam. Now, as you can see, this beam has a span of 20 feet, and we have a 10-pound load that is acting on the center of the beam. So because this 10-pound load is acting at the center of the beam, both ends, the end to the right and the end to the left and the end to the right, must equal to this 10 pounds. And because this 10 pounds is acting at the center of this beam at midspan, the reaction here, the reaction on this end is going to equal to 5 pounds. And the reaction at this end is going to equal to 5 pounds. So as you can see, 5 pounds plus 5 pounds, we get back our 10 pounds in order for the beam to be in equilibrium. Because the load that is coming down must be equal to the loads that are going up. So the reaction to this 10-pound loads, we have 5 pounds acting on the left and 5 pounds acting on the right going upwards. Okay? So I'm going to plot now the shear force diagram and also the bending moments diagram and show you what the calculation comes up to be. So our shear force diagram is going to look something like this. Right? And notice we have 5 pounds going up. So let's say for argument's sake, our 5 pounds come right there. Right? And we go across here, so we have to bring down this center line here. Right? So we have 5 pounds going up, so the 5 pounds come right here. And of course, this is our shear force diagram. Right? So we draw this across here. And by the way, if the beam span is 10 feet, that means if the beam span is 20 feet, that means we have 10 feet here and 10 feet right here. Right? So it goes across here. But you notice we have a 10 pound going down. So we have 5 pounds going up and we have 10 pounds going down. So from here to here is 5 pounds. That's 5 pounds. And we're going down 10 pounds, so we have to go down an additional 5 pounds. Right? So we have 10 pounds right here. negative 10 pounds. And by the way, the top is positive and the bottom is negative. So we come across here now, right? And you notice we have another 5 pounds going upwards. 5 pounds. So that is our shear force diagram. And of course, the distance here is going to be 10. It's going to be 10 feet. And the distance here is going to be 10 feet. 10 plus 10 to get back over 20 feet. Right? So this is our shear force diagram. Now, our bending moments diagram is going to look something like this. Because it is a point load. So imagine, as I've demonstrated to you earlier, this is the beam and the load is acting at the center. So the beam is going to tend to behave like this. So at this point here is going to be our maximum bending moment. Right? So to calculate the maximum bending moment is going to be the area of this rectangle, or the area of this rectangle, since the shear force diagram is symmetry, right? So the area of this rectangle is going to be, so the area is going to be 5 pounds here by 10 feet. So it's going to be 5 pounds. And remember now, because we have this 5 pounds here going upwards, and the length of this rectangle is 10 feet, so we're going to have 10 feet right here. So the area is going to be 50 pounds foot. So the bending moment here is going to be 50 pounds foot. So that is our bending moment. That is our bending moment. So the bending moment is going to be equal to 50 pounds foot. Now, as you have observed, that in order for us to get this 50 pounds foot, we have to calculate the shear force diagram, and we have to calculate the bending moments diagram. So we draw the shear force and we draw the bending moments, and we find the area of our rectangle here, which is 5 pounds times 10 feet, which is 50 pounds foot. That is how we get our maximum bending moment. So we have to do all of this to get this 50 pounds foot. Now, if you know the formula, you do not have to go through all of this. But this is still a good practice, because you're going to need this when you have more complicated beam system to work out, right? But if you know the formula here, you do not have to go through this. And I've demonstrated to you before that the formula to calculate the maximum bending moment for a point load is PL over 4. So I'm going to show you now, if I use this PL over 4, I can come back to my 50 pounds per foot without have to go through this. So if you look at it, you have the bending moment, which is equal to PL over 4, right? So if you notice now, if you observe, the load here is 10 pounds. So we have 10 pounds right here, times L, which is 20 feet, PL, 20 feet, over 4. So this is going to be 10 times 20, that's going to be 200 pounds foot. And we're going to divide this by 4, and we come back to our 50 pounds foot. See? So all I'm saying, if you know the formula, PL over 4, you do not have to do this. So this is, the formula is just a quicker way how to get the maximum bending moments. So in my next video to come, in my future videos to come, I'm going to show you how to use this bending moments here to calculate the amount of reinforcement or the amount of rebars to go into this beam to withstand that 10-pound force. But that is for future videos. So I'm going to stop this video right here. So if you have any questions, make sure to give me a comment in form of a question, and I will be more than happy to answer your question. As usual, if you're watching my channel for the first time, ensure to subscribe, hit the thumbs up button, and give me a like. And I'm going to catch you in another video. The next video, I'm going to be taking you through how to calculate the shear force diagram, the bending moments diagram, and also how to derive the formula for a uniform distributed load. So this video is for a point load. The next video is going to be for a uniform distributed load. Thank you. Enough respect. Catch you again. Enough respect.